Today, I want to go over some of the stuff we talked about before because it's been such a long time. So we're going to start on word problems, and in section 6.2, this is one of the finest applications of calculus. So I'm using last year's notes. These notes are all posted, so my job is to explain the notes to you, to guide you through them, to make you feel comfortable. Okay. So suppose I have 200 feet of fence. I want to enclose a rectangle. This is a perfectly fine industrial problem. That is the, the maximum area I can enclose. Okay, so we're going to make a rectangle. We're going to try to enclose an area, and we want to enclose the maximum area. So that is, what should the dimensions of this be? What should the dimensions of the pen be to enclose the rectangle of maximum area? So let's do a little experiment. We can start with 99 feet on one side and 1 foot on the other side. And then I enclose 99 times 1, 99 square feet. Does that seem right? Well, no, it really wouldn't seem right to anybody. And in fact, you can look down here a little bit better and get 98 by 2 as a dimension, as the dimensions. And if I multiply 98 by 2, I get 196 square feet. So somehow what I want to do is not just experiment like this. If you do this, you'll probably find something like the answer. Okay. In this case, you'll find the real answer because it's sort of set up. But basically, I want to find a systematic way to handle these problems. So somehow I want to make a picture like this. After all, why have I been teaching all this stuff? And then look for a local maximum. That will help me. Then I can guess, well, maybe that's the real maximum. And in these problems, it's always going to be, okay? So we want to try to make some kind of a picture of the kind we've been looking at and see if we can't find a local maximum in that way and hope that it's a global maximum. So there's a real trick here, and that is that in most of these problems, there's two variables. So if you try to solve this with one variable, you're sort of going to get a little bit squirrely, okay? Because you really x can be on one side. What is the other dimension going to be? You don't really know. So completely typically, we'll let y be the dimension on one side and x be the dimension on the other. Or x and y will be different quantities in different problems. Then let's look at the area of the square. That area of that square is xy, okay? So from the previous page, as I said, I want to find the local maximum and hope that it's a global maximum for this problem. There is a subject called calculus of several variables, but this is not that subject. And here I have an x and I have a y, and it's not very clear at all what to do. So why don't we try something? So the area is xy, and as I said before, I have two variables, and the perimeter of the rectangle is 200, okay? So what I can do is take this picture and write out that 2x plus 2y is 200. I have as well that the area is xy. And what I can do is get rid of one of these variables. This is completely standard routine. So we'll solve for y in terms of x, and then substitute, and then try to get a problem that involves only one variable. So let's see if we can do that. I have xy is 200, okay. 2y is 200 minus 2x. So everybody pay attention to the algebra. Don't divide the 200 by 2 or the 2x by 2 alone. You have to divide each of them by 2. So y is 100 minus x. Then we can put this back in the area equation. So the area is x times y. That area is x times 100 minus x. Now notice I've got only one variable, okay? So we're in calculus 1. And then this is 100x multiplied through by x. This is 100x minus x squared. Now I'll take the derivative and set it equal to 0. If I do that, I get x equals 50, right? 2x equals 100, x equals 50. When I put 50 back in this equation and play with it, I get y equals 50. So I had a 50 by 50 pen. Now you may have made some kind of a guess about this problem, so let's discuss it in general. In general, let's just take p feet of fence. So suppose I don't have 200 or 100 or something like that. We're just going to have p feet of fence, and I want to make a perimeter, a rectangular pen, x on this side, y on this side, with p feet of fence. So 2x plus 2y is p. xy, the area is xy, okay? And that's going to be equal to p minus 2x, okay? So y is p minus 2x. And when we solve, we have x times p over 2 minus x is the area. So the area, just like before, right, is p over 2x minus x squared. Similar to what was before. So the derivative of the area, a prime, is p over 2 minus 2x. So we set that equal to 0. So 2x equals p over 2. So x equals p over 4. Well, if x equals p over 4, when I put it back in the y equation, I'm going to get y equals p over 4. So I get x equals p over 4, y equals p over 4. Look at this, right? That's a square. If I have a square, then each side is 1/4 of the perimeter. And so I've showed you from that one rectangle problem that something you might have guessed if you thought about it, that the maximum area that can be obtained from a rectangular shape is if you make a square.